So dear students, today I am going to start a new topic, that is quantum mechanics. And this is not only a topic, you can say, or a branch of physics, but it's itself a new subject. Okay, so quantum mechanics is not a branch of physics, it is itself a complete subject, and it is the founding basics of all modern physics like solid state physics, atomic physics, nuclear physics, statistical mechanics, etc. all the modern physics. Okay, so it is the founding basis of all modern physics. And not only this, but it is the founding basis of the subject chemistry and biology also. So you can understand how important this subject is. And what we are going to start from today is a highly demandable and an important subject. And mostly the physics students are most excited actually when they are going to start this subject, quantum mechanics. And obviously there are various mystery, there are various interesting situations, there are a lot of exciting explanation, all are here in this subject. So now let me tell you that why this subject is very different from the other subject, basically from the other kinds of mechanics. Because when you are in a position to start the quantum mechanics, then I can assume that you have already studied about classical mechanics. So there also we have came across a term, that is mechanics, and here also we have a term mechanics, because classical mechanics has the end term mechanics and the quantum mechanics also have the end term mechanics. And what actually we have studied in mechanics, if you understand that what we are actually interested to know about mechanics, actually we have studied in mechanics system of particles. So in classical mechanics we have studied about system of particles, and in quantum mechanics we will also study about system of particles. But there is a basic difference between the properties of this particle, or the nature of this particle, or you can say inherent nature of this particle. And this inherent nature of the particle is actually due to their mass. The difference between the classical particles and the quantum particles is actually from their inertia. The classical mechanics is the classical particles, the system of particles which we have studied in classical mechanics have very low, actually the particles which we have studied in classical mechanics have very large inertia, have very large mass. But in quantum mechanics what we are going to study, the particle have very tiny mass, very low mass, so they are very low inertia particle. And why this inertia makes them so different, we are going to investigate. Why the large inertia particle, the heavier particles that we have studied in classical mechanics, and the particle that we are going to study in quantum mechanics, that is the very low inertia particle, or the very less mass, or the very tiny particle, why they have inherent difference between their properties for their mass? Because this is all about the process of observation. So if you remind in your classical system how you study a classical system, to study the classical system, first of what you have to know the initial two boundary condition, that at t is equal to 0, what is the position of the particle and what is the initial value of the particle. So without knowing the initial position and the initial velocity of the particle, you cannot solve the famous Newton's equation, that is F is equal to ma, because this is a second order differential equation. F is equal to ma is the second order differential equation, which is popularly known as Newton's equation. So to solve a second order differential equation, you have two constants, and to solve and to find out the value of two constants, you need to know two initial boundary conditions. And that boundary conditions are at t is equal to 0, the position of the particle, and at t is equal to 0, the velocity of the particle. That means the initial position and velocity of the particle, and that is called the initial state of the particle. So in classical mechanics, when we have studied classical mechanics, actually we always know the initial state of the particle, because we can observe the particle initially. If I ask you, suppose a particle is moving from this point in classical mechanics, if I ask you in classical mechanics, if I ask you a particle is moving from this point to this point, a particle of mass m is moving from this point to this point, then by using the coordinate system as you choose, you can tell me the what is the initial position and the initial velocity of the particle by observing the particle, simply by observing the particle. If this is a bus stop and a bus is standing here, if a bus is standing here, so you can tell me the initial position and the velocity of the bus just by seeing this, just by observing this. And the process of observation does not affect the initial state of this object or of this bus or something like that, any kinds of objects. And what is your process of observation? Your process of observation is that a light is shining on this object, light is falling on this object, and from this object light is reflected to our eyes and we can visualize the object. So to observe any object, you have to interact with something called radiation or something called light. So whenever you are going to observe any system in our real world also, whenever you are going to observe any system, you have to interact with this system with light. And the process of observation, that is interaction of light with this object, does not affect its positions, its initial position or its initial state. So in classical system, due to its mass is high, as this is a large inertia particle or this is a high inertia particle, as the inertia of the particle is high, that means the mass of this particle is high. So the process of observation, that is the interaction of light with that object, does not affect its initial state, because it's a high inertia, and the energy of light cannot disturb this high inertia particle, because its rest energy is much greater than that energy of light, and this is due to its mass, its inertia. So the particle does not affected by the process of observation, and that's why we can definitely say what is its initial state, that is what is its initial position and velocity. We have the boundary condition, and that's why we can apply the famous Newton's equation F is equal to ma. F is equal to ma, because this is a second order differential equation. To solve this, we need to know two initial boundary condition, and that is the initial state of the particle. And then after time t, what will be its velocity, what will be its position, we can definitely understand, we can definitely calculate from this equation. But in quantum mechanics, what will happen? In quantum mechanics, what will happen? This mass of this particle is very low, that means it is low inertia particle, and when you want to observe this particle, you have to interact with light, and the process of observation, that is interaction of light with this matter, will disturb its position. So you cannot definitely say its initial state, that is its initial position and its initial velocity, you cannot say its initial state. So it is something impossible to know the initial state of this object, and that is the inherent uncertainty of this particle due to its low inertia. This is the indeterministic nature of this microphysical world, that is something like atomic system, subatomic system. So you cannot tell its initial position and initial velocity definitely, you cannot say its initial state. So whatever you are seeing or you are observing by anyhow, whatever you are observing, it's not its actual state, its true states, because its states is changing due to this interaction. So there is an inherent uncertainty of the system, there is an inherent uncertainty of the system, or you can say there is an inherent indeterministic nature. and that is why we cannot apply this F is equal to ma for this particle. So we have to establish a new kinds of formulation, and with that formulation we can calculate its later state or its initial state or something. What will be its initial state, how we can predict, and there are lots of things will be coming like probabilistic interpretation, etc., etc. Lot of new things will be coming here because its initial state is not known, and that is the basic things, that here the process of observation does not affect the observation, but here the process of observation is affecting the observation, and that's why you cannot say its initial state of the particle, and that is due to the mass. And that's why for low inertia particle we have to formulate another kinds of mechanics called quantum mechanics. But at the beginning of 19th century, scientists thought that the whole mystery of universe they have known. They thought that the then existing theorems or the phenomena, all the existing phenomena or the theorem, how nature operates, they can understand and they can explain by Newtonian mechanics, Maxwellian electromagnetic theory, and the thermodynamics, then existing phenomena thing. They thought that they can explain all the things by using that existing theory. But when new technology comes, several new kinds of experiments are done, like photoelectric effect, black body radiation, etc., etc. We will discuss about Compton effect. We will discuss all these historical important experiments that will actually tell us why we need to invoke a lot of concepts to establish the new science called quantum mechanics. We will see in this chapter. In this chapter, the first chapter, that is the origin of quantum mechanics, we will see these experiments sequentially, one by one, and why we need quantum mechanics, why we need to establish the new kinds of mechanics for the low inertia particle. We will see in this course, in this chapter actually, that the origin of quantum mechanics. We will discuss about the particle aspects of matter, we will discuss about the wave aspects of matter one by one. Okay, so this is your introduction class for quantum mechanics, and I think this is enough for introduction, and we will discuss a lot of new things and exciting things in this course. Okay, so please subscribe my channel to continue these videos, to get the notifications, okay, and to grow this channel, because your supports will be the most important, how I will be more energetic to do you more exciting video that are going to come in quantum mechanics. Okay, thank you.